On page 35, you'll find a bunch of examples that are very similar to what you saw on page 34, with the goal of connecting, if possible, the units that we're exploring in each real-life scenario to the antiderivative, or at least the significance of the antiderivative in the context described. For example, in question number 7, it's a question that gives you some data about acceleration and asks you about velocity. Well, we know, because we've seen this connection before, that the derivative of velocity is acceleration. Therefore, the antiderivative of acceleration is velocity. So instead of finding an antiderivative, we're going to do an area problem. So remember the connection there. Antiderivative is now synonymous with area, just like slope is synonymous with derivative. Antiderivative is synonymous with area. So by finding the areas of each of these regions underneath the acceleration curve, we're going to be able to estimate the velocity. It's not going to be a great estimate because we're going to be using a left Riemann sum, and just like you saw on page 34, rectangles don't exactly give us a super accurate representation of the area itself, but it's going to serve as an estimate, a close enough, if you will. Now, because question number 7 is asking about a left Riemann sum, and we've already done a left Riemann sum in the example in the previous video, I'm purposely going to choose an example to do on page 35 that has a different type of calculation so that you have a bit more variety. Question number 8 uses trapezoids, so that one, again, we've tried before. I already kind of feel like you might see that if you watch the previous video and get an example. So I want to do question number 9, because question number 9 is about a right Riemann sum. And I think that a right Riemann sum is going to be a slight twist, but in a way that we might want to see together through an example before I set you off on your own to do the rest of the problems on pages 35 and 36. So as you're taking a look at the data here, the first thing that you'll want to remind yourself of is that we need to create a picture. In the previous video, you saw on page 34 that we were given an axis or an XY axis set to plot the points on, and in this context we're not. This is actually more common to the way that an FRQ or a college calc question would appear. They very rarely give us an axis to plot our points on. It's our responsibility to create one. So I would recommend, if you haven't yet, find a bit of scratch space, so maybe an extra piece of scratch paper, whatever you have that you can work with, and use that to create your graph. If this was an FRQ type situation, they would expect you to actually create your graph in the answer space provided in the little booklet that you'd be writing all your answers in. So making the graph is definitely a mandatory step. Even if eventually you get so good at Riemann sums that you don't really need to make a graph, I still recommend it, because there's something about the graph that just taps into our more base instincts. Like, we understand area. When we see the area, it clicks to us and we're like, oh, base times height, I got it. And I found that sometimes even though shortcuts and little tricks for doing a Riemann sum quickly do exist, sometimes it strips away that feeling of, oh, I understand what I'm doing. And then people get things wrong because they apply this magical little shortcut. They get an answer that doesn't really mean anything to them, and they can't really tell if the answer is wrong. You know if you do an area problem wrong because you've done so many areas before that you already can kind of tell, like, oh yeah, that looks right. So that's why I'm always going to recommend, even if you feel like you don't need to, try to make a graph. I know it can be kind of tedious, but it really is worth it. When it comes to making your graph, it doesn't need to be very rigorous. It doesn't need to be perfect. It's basically for scratch work purposes, but try if you can to keep yourself vigilant about 2 things. First, clearly labeling the points, because we know that we're going to end up needing clearly labeled points in order to create all of our rectangles. And secondly, clearly labeled axes, because the units on each axis are what ends up giving us that way of making sense of our answer at the end. So if we go back and reread question number 9 a little bit more for detail, it's talking about coal gas produced at a gasworks, which is just a fancy way of saying that's where coal gas is produced. The pollutants are being removed by scrubbers. This is starting to sound like a science question, so I'll summarize here. The measurements indicate the rate at which pollutants escape, measured in tons per month. So time is our independent variable measured in months, and rate of escape is in tons per month. You'll find that the AP in particular loves context-rich questions like this. Don't get yourself trapped in the rabbit hole of thinking, rate of escape. How do pollutants escape? What would that look like? What's a gasworks? Can I picture a gasworks? Because that's exactly where people get so bogged down in the minutia of the question that they stop thinking about the calculus. Even if you're fascinated by the situation, try if you can to focus on the goal at hand. We need to plot some points, we need to create some rectangles, and we need to find a right-hand Riemann sum. So we're going to first label our axes. The independent or x-axis is going to measure all the times, and I always like to measure and include relevant units, so months. The y-axis is the rate of escape. I'm just going to call that a rate just because that's a nice mathy word. And then, of course, our units, tons per month. So that way I have a clear set of labels to work with. Now, as it stands, I don't need to make a perfect graph. I just need a good visual for what I'm going to try to calculate area-wise, which means I really just need to label my x and y coordinates carefully, because the x and the y coordinates dictate the base and the height values for my eventual area calculations. So when time is 0, we have a point at 5. Now, if you're wondering where exactly to start looking for that first point, like how to scale your axes, I would just look at the numbers and say, okay, well, the smallest number appears to be 5. The biggest number I need to plot on the y-axis appears to be 20. So that's kind of giving me a sense that the highest number needs to be 20. So roughly a fourth of the way up there would give me 5. So I'm just going to plot this point at 0, 5. Remember, I just like to kind of casually label. You don't need to write parentheses 0, 5 parentheses. Just keep it as simple as you can. Now, of course, we're going to keep labeling, figuring that the x-axis is eventually going to go all the way to 9. So I'm at 1, 2, 3, 4, 5 at the moment, and I'll keep labeling 6, 7, 8, 9. I do like to label those just because you can tell that those time values are going to jump in kind of a weird way. So I like to label those individually, but that's obviously a personal choice as well. So the next point is at 1, 7. That's not going to be much higher up than the previous y coordinate we already had. So I'm just going to estimate a rough location, but I'm definitely going to label it 7. And then I'm going to repeat the process for each subsequent dot. 3, 8, which is again only a little bit taller than the previous one. 4, 10, a little bit higher up from there. And then 6, so notice we're jumping here. 6, 13 is a bit of a jump up. Apologies that I'm not scaling this particularly well. So if the distance between these points is bothering you, feel free to make a better graph. 7, 16 would be a little bit higher than that. And of course, 9, 20 is all the way up in a poorly scaled way, somewhere up here. Now, I've apologized about my scaling, and yet I do need to make an important concession here that I'll admit I was probably a little bit too casual about acknowledging. The gaps between these rectangles are no longer consistent horizontally. If you look at it, the dots go from 0 to 1 and then 1 to 3. So when I make my rectangles, I do actually need to keep that horizontal spacing in mind. And even though I'm not going to label that horizontal spacing, you can probably tell why I labeled my x-axis with more rigorous coordinate sets, because, or at least tick marks, because we're going to need that distance in just a moment. Now that I have my curve, and I can kind of estimate, it's probably going to look something like this. Again, time is a continuous value, so you can infer that this is a continuous function because there's obviously going to be a half of a month, or 1.5 months, or 7.5 months, and it's quite possible to estimate the actual rate of escape at those times. But they obviously didn't give us those data points, which is why I'm just going to infer a continuous weird looking curve, but I'm not going to nitpick too much about what it might look like because they just didn't give us enough data to know for sure. In any case, we need to create a right Riemann sum to be able to do this area approximation, which means I'm going to start on the right-hand side of my graph to create my rectangles. Remember how on the previous video on page 34 we started on the left-hand side to create our create our rectangles? I always recommend starting on the side of the graph that corresponds to the type of Riemann sum you're going to create. So if you're creating a right Riemann sum, start on the right-hand side of your graph and start making rectangles from there. To create this first rectangle, I need to make sure that this point at 20 is the right-hand corner. So I'm going to extend my rectangle top all the way out to roughly where it looks like the next rectangle would end up taking over. So notice I always stop roughly lined up with the next data point, and then I'm going to drop the height straight down. I do want to try to do the best I can. Ugh, terrible. But I want to do the best I can to make sure that the area or the height of that rectangle and the base of that rectangle are roughly correlated to the x coordinates to which they belong, so that I can clearly estimate that width of the rectangle. And again, apologies, this is super wobbly. Now to create the second rectangle, I'll go to my next data point at 16. I'll extend horizontally till it looks like the next point would take over, and then down. I'm not doing a great job of drawing to scale, to the point where I have to confess this is actually bothering me. But once you get to the point where you can start to see these rectangles are different widths, that's going to be an important concession. Oh, no wonder. Not even close. It's going to be an important concession to make, because when you're finding your areas, some of them will have different bases and obviously different heights. So again, the moral of the story is be as careful as you can. Now I'm just going to repeat the process, doing the best we can to keep creating these right-hand rectangles. So from my data point, extend the top of the rectangle out till it reaches the next dot, and then drop your height down. Then the next one, out, and then down. Then the next one, out, and then down. And the last one, out, and then down. You will have one unused data point, just like we had before, because you'll recall that this last data point would be a right-hand rectangle that extends past our interval, which doesn't make any sense in context. We wouldn't have any negative time values, so this point at 5 is not going to be used as the right-hand corner of any of the rectangles we need. Now we're going to find all of our individual areas, and this time we just need to be a little bit more careful, because not all of the rectangles are consistent in width. We actually have to be a little bit more careful about this one. Now you can start wherever you want. I always like to start on the right hand side for a right Riemann sum, but it's totally your choice. I'm going to start on the right hand side though, and I'm going to look at my base. The base is 2. The height of this rectangle was predicated on the y-coordinate from the original point that I drew the rectangle from. So the height of this rectangle is 20, and base times height ends up giving us an area of 40. If you make your own diagram, sometimes you can make it big enough that you can actually write the area values inside of the shape, which I totally recommend doing, because it will help you organize your information, especially once you're done. So I'm just going to go through and do each area. The next one has a base of 1, because notice from 6 to 7, that was the entire width that I needed. And the height of this rectangle is predicated on this right-hand corner, which was 16. 1 times 16 has an area of 16. And you'll notice I'm just circling my areas as I go, so that way I can tell when I'm done which ones I'm going to add up. The next rectangle has a base of 2. Its height is 13, so its area is 26. The next rectangle has a base of 1, a height of 10, so that area must be 10. The next rectangle has a base of 2, height of 8, its area must be 16. And the last rectangle has a base of 1 and a height of 7 for an area of 7. Now that I've seen all of my areas, I can quickly sum them up. So just for the sake of doing something a little bit faster, I'm fine with you using a calculator for this task. Although I should make the disclaimer that oftentimes on the AP test, a calculator would not be allowed for such a problem. It's not the worst thing in the world to have to do this area calculation by hand, but it's just worth noting that for practice purposes, it's totally okay to use a calculator. So the sum of all of the areas is 115, which must be my answer. My answer must be 115. I have no context whatsoever for whether the real answer is even close to 115, but I can infer just based on my graph, this is probably an overestimate, because notice when I drew my rectangles, many of them popped up above my estimated curve. So chances are the real answer, if we were to actually get a proper function and do a proper antiderivative, is going to be less than 115. But nevertheless, we know that the answer itself is 115, but let's deal with the situation regarding units, because the units are part of a good answer and will help us make sense of what 115 really represents. I'm again just going to focus on one of these rectangles for a second, and I'm doing this little arrow just to show I'm redrawing one of them. I'm only doing this for illustrative purposes. You don't have to actually do this part, but it might help you make sense of what we just did on this rectangle at the very far right hand side of the diagram. I'll kind of shade in the one that I'm talking about. When I measured its base of 2, that was the gap between month 7 and month 9 on my graph, and because that gap was measured in months, we know that the base of each rectangle was a value of months. When I got that the height was 20, the 20 was the y-coordinate that represented the data point of tons per month. So again, just in terms of relevance there, tons per month, sorry, not plural, is going to be my y-coordinates unit set. So when I did my area 2 times 20, I was doing 2 months, and I'll not make it plural there just so that it cancels out, times 20 tons per month. Again, you can think of this like a stoichiometry problem, if you remember what that word means, because when I multiply these quantities together, it's almost like this is all over 1 and this is over 1, if you want to think about it as a true stoichiometry problem. The months are going to cancel out, and that's the part that's so important. The months cancel. So when we do 2 times 20, the only relevant answer that's left, units-wise, is tons. And that means that in that gap of time, in that span between month 7 and month 9, I must have emitted 40 tons worth of pollutants. And that means that each of these answers was the number of tons of pollutants that escaped every month. In the gap between months 4 and 6, we lost 26 tons. In the gap between month 3 and month 4, we lost 10 tons. So when I added up all these numbers, 7 and 16 and 10 and so on and so forth, I was adding tons plus tons plus tons plus tons. So the sum total, 115, is the sum of, or the total of, all of the tonnage we lost. So that means that the 115 really is how many tons have actually escaped in that 9-month span. When I write my answer, I am actually going to say it as 115 tons. Because when you read the question back to yourself in context, it actually does make sense. It says, use a right-Riemann sum to estimate the total number of tons of coal removed, 115 tons. It seems like we're answering the question quite appropriately. So for all of these questions, do try, if you can, as part of maybe your side work, to show this little stoichiometry. Eventually this will happen more naturally, and eventually it will get easier to predict the units without doing this more official unit analysis. But as we're getting used to the idea, I recommend showing it. It won't be required on things like tests in the future, but I do recommend as part of your practice keeping it in mind, because it'll help you develop that instinct that eventually will become a lot more natural with time and exposure. In the interim, between now and when we resume next week, remember, is spring break, so I'm saying next as in 2 weeks from the date of this recording, which is week 29, we'll resume our next set of problems in a new packet, and that will extend this idea of Riemann sums further. So if you finish page 35 independently and page 36, which is more Riemann sum practice, practicing drawing graphs and drawing the diagrams so that you can calculate the sums, you'll notice after page 36, it actually switches to just basic random practice of stuff. So the end of the chapter is essentially this concept of Riemann sum. When we follow up in the next school week, so again, week 30 is the week after what would have been spring break, so essentially March 29th, if you want to think of a calendar date, that's where we'll officially start a new unit. And in the new unit, we'll take this kind of concept and we'll run with it even further. We'll start to see why we use Riemann sums. We'll start to connect it to actual antiderivatives, stuff like that. So just to make sure that you're going to be in good shape for the beginning of a next chapter, make sure that you do all of page 35 and check your answers. These are the most crucial problems that you can do to get yourself in good shape. If you have time for page 36, it's a good idea to do so, but try if you can to just focus on page 35 for now. Make sure that you're good there, and use page 36 for more just like plotting and drawing practice. Nothing more than that. As always, the answer keys are posted in our learning plan. Please use them. And if you have any questions, don't hesitate to send me an email.